Alright, hi you guys. Today we will be talking about related rates, and I wanted to spend some time just getting into this and just working with it. Okay, just from refreshing my brain from before, I really tried to struggle with the idea of how to teach related rates, and especially over video. And I came up with these methods from several sources. One is, I believe it's Integral Calculus. And it's an integral calc, and it's on YouTube. Great video, really easy explanations. They really work it out and just show you all the stuff. Okay, so the first thing you have to do is identify what you have and what you need in related rate problems. Okay, so let's say that we were looking at this problem. Air is being pumped into balloon at 10 centimeters or 10 cubic centimeters per minute. Calculate the rate at which the radius of the balloon is increasing when the diameter is 15 centimeters. Okay, so the things we know are, we know the formula, we know the rate at which the balloon is increasing, so it's that bad boy right there. Okay, we also know the radius, which is half the diameter, so if the diameter is 15, then the radius is 7.5. We just don't know the rate at which the radius is increasing. Okay, so we know that stuff and we know what we need. Okay, now what we're going to do is set up and plug in. Okay, so we set up the problem, and what we're going to do is we're going to do integral or implicit differentiation and differentiate with respect to t. So that means we're going to have a dv slash dt here and a dr slash dt here. So when we integrate, this turns into 1 times dv slash dt, because you know the integral of a number is just is 1, so it's just going to become dv dt. Alright, and the integral of this is going to turn into 4/3 pi, which is the constant, times 3r squared. Okay, alright, times dr dt, because implicit, when you differentiate with respect to another letter, you have to just write that down implicitly. Okay, so now we have it all written out, and then we simplify it. The 3's cancel out, and we're left with dv dt equals 4 pi r squared times dr dt. Okay, now if you notice, we have a couple of gaps. If you think about this in terms of, okay, now we know some values, now I can plug it back in, I'm good. We know dv dt, that's 10, so we can plug a 10 in there. Okay, we also know r, which is 7.5, so we plug a 7.5 in there. Now if you notice, we have everything but what we need. So all we do is do some calculations, and we get this, and at the moment at which the diameter is 15 centimeters right there, and the balloon is increasing at 10 cubic centimeters per minute, our rate of the radius expanding or increasing is this, 10 divided by 4 pi times 7.5 squared. You can actually simplify that. I believe this is going to be well, shoot, let me calculate it. So we got 4 times 7.5 squared, 225. So it's 10 over 225 t, or pi. Sorry, 225 pi. Okay, so you know it at that moment. Now, if this had changed to 20, this would change to 20, and I would have a different answer. Okay, so it depends on what the size of the balloon is, how big it's going, how fast it's increasing. I mean, just everything is doing it to it. So the first step was identify what you have and what you need, set it up, and plug in your formula for differentiating. Take the derivative and then plug in the numbers and then solve for what you need. Okay, it's as simple as that. Alright, now the next page is talking about the ladder problem, the infamous ladder problem. A 45-foot ladder is leaning against a wall at the top of a sliding, and the top of it is sliding down the wall, while at the bottom slides away from it at a rate of 5 feet per second. How fast is the top sliding when it's 12 feet from the ground? Okay, so the ladder is 45 feet tall, and we make our triangle picture, and the height of the ladder at that moment is 12 feet above the ground. Okay, we just don't know how far the bottom is from the ground from the wall. Okay, so the ground squared plus 144 equals 2025, and when we solve it, it's 43.7 feet by using Pythagorean theorem, which makes sense because that should be smaller than that because that's the hypotenuse. Okay, now what we're going to do is we're going to use the same exact formula, and we're going to use Pythagorean theorem as our beginning formula for it. Now, we don't know the height at which it's decreasing. We do know the the rate at which it's going away from the wall, and that's 5 feet per second. We know the height is 12, and we know the ladder's length is 45. So we replace A with G, or you could replace B with G, doesn't matter. And we replace H, we replace B with H. Okay, now what we're going to do is differentiate with respect to time. Okay, and so we get 2G times dG slash dt plus 2H times dH over dt equals 0, because remember, when you differentiate this, this becomes 0. Okay, and then we just plug in the numbers. We know G, the length from the ground is 43.7 feet, so that's why this becomes that. We know that dG over dt is 5. We know that the height is 12, so we plug that in, and we don't know the height at which, or we don't know the rate at which it's decreasing its height, so we just kind of calculate it. We get 437 plus 24. Then we move it over here by subtraction and division, and we get negative 437 divided by 24, and we should get negative 18.221 feet per second. And this is the rate at which the height is decreasing. Okay, and so the sign is hugely important in related rates because it will tell you if it's increasing or decreasing, and thus telling you a good story about what's going on. Okay. All right, if you have any questions, please feel free to ask, but these are two of the more widely used problems that you can do. So just identify what you have in need, set it up, and plug in. Take the derivative and plug it in after you get done doing the derivative, and then solve for what you need, and you can actually do this pretty well. Okay? You guys have a wonderful day, and I'll talk to you later. Bye.